But Sam is the principal software engineer of the generative AI team at DScout with a comp sci BS, an MBA from UTC, that's our University of Tennessee right over here, and a master's in comp sci machine learning from Georgia Tech. This led him to these experiences, working with time series data for CO2 and methane emissions, computer vision, data collection, and hardware adjacent clients at Very. He lives right here in Chattanooga, Tennessee with his wife, Ashley. Give it up for Sam.
Thank you, Brad. Awesome. So how many of y'all are watching this talk because you want to be rich? Just show of hands. It's everybody, right? All right. I am not that guy. This is not that talk. All right. So again, like, there's no guarantee that you're going to make money in the stock market. There's always a risk of losing money. Do it at your own risk. That being said, like, I took a class on it. We did everything in Python. And I don't know if you worked in Python, but it's not fun. So I wanted to know, how do we do this in Elixir? So what are we going to talk about? So we're going to talk about how do day traders make their choices? How do they know which positions to take with their stocks and their strategies? I'm not qualified to tell you like what your strategy should be, so I'm not going to talk about that too terribly much, but we'll kind of cover that a little bit. Then we're going to talk about like what does it take to get that into a model or a policy. Then we're going to talk about like how do you evaluate and pick your algorithms and how do you evaluate your results. So I'm really glad, Bruce, that you and Savannah went before me, because there's a lot that I don't have to cover now. There's also a live book. It was on the first slide. It will also be on the last slide. So this talk is very much just like give you the terms and then go look at the live book because it will make a lot more sense. So let's start with $1 million question. How do you pick your positions? How do you know when to go long or know when to go short? So we do this in trading. I say we, like I've done it professionally and I'm making millions. I'm not. But you do this with technical analysis. This is kind of like the Jim Simons approach and what they've done at Medallion. This is not the Warren Buffett approach, which is more fundamental analysis and looking at like a company's balance sheet and actually figuring out the value of the company. Technical analysis is taking price and volume information, because the theory is that all of the price and volume information encompasses the information of what is on the company's balance sheet. So what you end up doing is you pick several indicators based upon the data, which this is time series data. So this is really more of like machine learning for time series data, but you know, it's more interesting doing it for stocks. But you want to go through, you want to figure out what the trends are, how strong those trends are. You want to know the momentum of the stock as well and how strong that momentum is. You want to do some like cumulative window type calculations. It's a lot of math. Thankfully, NX makes it a lot easier, especially with like Explorer. You'll see in the white book that I use Explorer a whole lot as well. But the key is once you pick a strategy, be very consistent with that strategy, because you need to be able to evaluate the strategy. So if you modify the strategy, you're not going to know if it's working. So if you're going long, you want to keep going long the same amount whenever you go long. If you go short, you want to go short that same amount. Makes it easier. So, but the goal here is knowing when to buy, when to sell, when to go long, when to go short. And when in doubt, Investopedia is your friend. So definitely take a look there. So how do we get this data into a model or a policy? Well, we've already hit on stock data being time series data, but like what other kind of time series are we working with, like specifically in machine learning? Like if you look in Bumblebee, like what What is looking at time series data? Any guesses? How about natural language? Natural language is a time series of words. So let's just see if that'll work. Let's take a strategy. Let's get some price and volume data. Let's then compute the indicators. On top of that, we also need to compute labels because it's not going to be labeled data. So you do this by cheating. You have perfect information because you know the past. And you can look one day into the future and see, hey, the stock price went up, so I want to go long, or it went down, so I want to go short. So you want to create those labels. You're going to split this up into testing and training sets. And since it's time series, rather than doing like a 80-20 split and sampling randomly, you have to pick a date where you're going to split on. So that way you're looking at sequential data. Otherwise, you'll train on stuff in the future and then you'll get wrong result. You'll get false results. Then on top of that, like you're going to choose an algorithm, which we're going to look at RNN first, which is going to be a type of layer technique on top of linear layers. And then, we're going to iterate and improve the model. So on Axon, there is a guide for doing natural language processing for predicting like the next letter in a sequence of characters using a type of layer called LSTM. That stands for long short-term memory. And yes, this is a lot of math, but it's going to be okay. Basically, what's going on inside of these LSTM layers is you have the cell state, the memory, you have the input that you're getting, you're going to recurse over that, which is why it's called an RNN. It's a recurrent neural network. So you're going to recurse over the data. And then you have a hidden state. This is where the weights and biases come in. As you progress through the LSTM, what's going to happen is you're going to get to this first gate that's a forget gate. And what this means is how much do you need to know of the past to be able to predict the future? So what we're doing here is the input to this kind of layer, it's going to be a sequence of vectors, and the forget gate learns how many of those vectors do you need to look at? Or if you're working with like text, how many of those tokens do you need to know in order to predict the next thing? The input gate then is going to encode the input and add that to the memory, the cell state. Then it is going to use that to generate output. And then it's going to recurse and go back over. So what we want to do in modeling our problem at this point is we want to compute a bunch of these indicators. We're going to batch that with an X2 batched. So we're going to send, however many you want. If you want to send like 1,000 at a time in a batch, like that's kind of wasteful. You don't need that much, but like you can try it because you want to tune your model. So not too terribly bad. So first attempt is, let's just copy and paste what's up on the Axon guide. Let's not try too terribly hard. We've done a little bit of thinking into how we could solve this problem. We can compute all of this with Explorer. We can create all of these batches and compute the training labels. Like that part is easy, but does it work? No. So you don't want to do that. And honestly, like it's kind of comfortably that it doesn't work, because if you could just like slap AI on a problem, like we would all be in trouble. So, but like this is a teachable moment, and it's not failure. We're not quitting here. This isn't the end. But what we did was we optimized for a position in our training data rather than optimizing for returns. Returns were not taken into account because you're looking at the sequence of vectors and saying, I want to go long or short. So in training, the model had a 30% return, but evaluating on test set, there was only 2%. Like, you can get better in a savings account right now. So no point in doing that. But, you know, there is some evidence and some literature that these kind of techniques can work with time series data and be adapted from natural language processing. So it was worth looking into this particular case that didn't work. Just as an aside, like, I asked ChatGPT because I use GPT-4 for most of the work that I'm working on. And I was like, hey, like, can you give me like a starting point here? Use Axon and NX and Elixir, and it like spit out something, and it imported like the modules. I was like, I have no idea where this has come from. Don't import anything. And it was like, okay. So then it just like put Axon dot in front of everything, and then I went and I was like, that was too easy. So let me go look at the documentation, and none of those functions existed. So then I was like, where did you get this information? And it literally said Axon and NX are fictitious packages. So we're safe. It's all good. But like I said, you know, it's only failure when you quit. So let's talk about other techniques. And something that I've gone through that I really like working with is reinforcement learning. And in reinforcement learning, this is a very like stereotypical example of like what you will see in like an introduction to reinforcement learning technique. What we have here is we have an agent and we have an environment. And the agent will progress in the environment, perform actions until it gets to a goal state. This is the end of an episode, and then you're going to reset and you're going to train it again. So each of these episodes are comprised of experiences, and all that means is that an experience is a tuple. It has the current state, and the current state comes from the environment. The agent takes that information, determines what the best action is. The agent then receives a reward or a penalty from the environment, and then gets told what the next state is going to be, so that way it can go into the next action. And this is called a policy. In reinforcement learning, we are learning a policy. We're not learning a model, because these agents, you can throw them in any environment and they'll still learn and how to operate in that environment. So you want to know a policy for how to act within that specific environment. So that's the key here. So this really kind of like sums it up. Basically, like, you have two pieces of code. The agent operates, it has no knowledge of the environment other than it knows like, hey, like, this is how many states that I can have and how many actions I can do. And it doesn't even know like what the actions are. So like in the previous example, or on the previous slide here, like the actions for this agent to move to the blue square will be like 0, 1, 2, and 3. And the agent has no idea what 0, 1, 2, and 3 mean. It just knows that it can return 0, 1, 2, or 3. So the environment will take that information and then it will process that and generate the next state. It will transition the agent to the next state. The agent chooses the action, but the environment defines the transition and the rewards. So this is also known as like model-free learning, because you're not learning a model of the environment. There are some reinforcement learning techniques that do that, but we're not going to do that. So what is a policy? We've already kind of hit on this a little bit, but basically you have states, and at each state you can do an action. So what you do inside of your agent is you're told like, hey, I'm at state 1. Okay, well, I can index state 1, and then I can do the argmax on that vector of actions, and that's going to be the best action to take. Because what we're going to encode inside of this policy is the discounted future reward of being in that state and taking that action at that point in time. So what we want to do is we want to consistently like build our rewards, because we want to make money. We don't want to lose money. And then take the best action. So this is called Q learning. And in being able to update this policy, you have to do a lot of math. And I'm very sorry, but this is very not that bad. So we're going to walk through this very quickly. So we start out, we've got Q of SA. So in math, capital letters mean matrices. Matrices are 2 by 2. S and A are indices into this matrix. Now we've got an arrow that's not equals, that's an update. So we're going to update the policy, but we're also going to update it by indexing QSA. So real quick, what does that look like? Close. Yes, it is recursion, because this is a dynamic programming technique. What we're doing is we're keeping track of history in our policy, and we are recursing over that information. Now, what we want to do is we want to know at this current state action pair, what is the discounted future reward? So what we're going to do is we're going to incrementally learn. That's what alpha is up here. We want to learn just a little bit, because otherwise it gets very chaotic if you're just completely like overriding everything. Then what you're going to do is you're going to take the reward, and then gamma here is the discounted next reward. So then that way you know, like, hey, I'm going to end up in this next state. What reward can I expect to get by getting to that state? Then you're going to subtract your current Q value, which Q stands for quality, so that way you don't double count it. And that's really like what that looks like. And in looking at the live book, all of that is this right here. This is just pure in X. It's not, too terribly bad, I don't think. But basically we're saying like, hey, pick the best action. We want to take, Q of SA times 1 minus alpha. So that way we don't over account for it. And then this improved learning here, this is, plus alpha and everything after that. So we've got that. We know how to update the policy now, but we also have to define the environment. So if you're just like going through a reinforcement learning like tutorial or something like that, they usually have you install a Python package called Gymnasium or OpenAI Gym. And what these are already like pre-built environments for you to be able to experiment with these algorithms with, so then that way there's a consistent way to compare them. But for this problem, we have to define the environment. The environment is not defined for us. So what we need to do is we need to simulate buying and selling a stock. We have to control progressing through time. Thankfully, we're not like moving in multiple directions. Every action takes you to the next day. So that's a beautiful thing about time series. Then after that, we're going to tell the agent like, hey, here is the current state. Tell me what action you want to do. And then we're going to simulate all of this. So in simulating this specifically in like a stock kind of setting, every time you make a trade, the market moves against you. So you want to simulate that as like impact, which is in this formula here going to be I. H is going to be how much of the stock that you're holding. P is going to be the price of that stock. F is going to be your fees for trading. This is usually like $9.95 if you're using like Robinhood or E-Trade or something like that. And then C sub I is your current cash, because we have to keep track of our portfolio, and our portfolio value is cash plus holdings times the adjusted close. That's what this C adjusted is down here. So you calculate this every day. You take the cumulative sum in order to figure out how much cash you have. You compute the value of your portfolio, and the returns that you give the agent are the daily returns. So if the action that you took resulted in the next day the price of the stock went up, you know, hey, like you're going to get that dopamine hit. You're going to get that reward that says like, hey, you made money. But if it goes down, it's going to correct and say, hey, like that state action combination is not that valuable. Don't do this. Now, what are some problems with this that we can think of? So if you start at episode 0 and you perform an action and you go through that entire episode, at the next iteration, the next episode, if you always take the greedy approach, you will continue to select that action if it was a good action, and you won't learn another path through the environment. So in reinforcement learning, we call this exploration versus exploitation. And what that means is that in the beginning, you don't know anything, so you have to mess around and find out. As you mess around and find out, the more you mess around, the more you find out. We want to exploit that once we know something. So how do we handle this? This is called epsilon decay. So what we do is we initialize epsilon to a very like close to 100%, like 99 or 999. And then we have a variable called epsilon decay, and that every time that we take a step in the environment, we're going to multiply the epsilon decay by epsilon to reduce the percentage that we want to perform a random action. You're going to pull a random uniform number, and if that number is less than epsilon, you're going to do a random action. You're going to explore. So over time, as you progress through the environment, you're going to transition from exploring into exploiting and like actually learning the environment. So in stocks, like when we compute these indicators, they're all continuous values. So that is a problem because you can't, like, what is like Q of 1.1? Like what does it mean to index by like 1.1? So what we have to do is we have to convert these values into bins. That's also demonstrated in the live book. And all that you do is you break it up into like chunks of 10. So then that way you can encode those like 0 through 9. And you have to do that for each of the indicators that you're looking at. You want to look at more than one indicator because you want confirmation of a signal. And in order to do that, like your first indicator will index like 0 through 9, but your next indicator is going to be 10 through 90, or sorry, 0 through 90 in steps of 10. So what we're going to do is we're going to add all of those numbers up, and we get a lot more states. So like if we're looking at one indicator, that's 10 states. 2 indicators is 100, 3 is 1,000, and so on. It keeps multiplying by 10, it's exponential. So that becomes a lot to keep track of in memory. Not to mention, we also lose a lot of information from our indicators because we're just saying like, hey, chunk this into the 0 bucket. So what you can do to get around that, if you have a very large state action space, is you can do deep reinforcement learning with Axon, which I tried to do, but I'm not a smart man. I couldn't get it to work, and it's because like part of the update environment in the loop is you have to perform a prediction, and NX just returns the expression at that point, and it was very upset with me. It was like, you can't index into this expression, and I was like, just give me the number. So it was not my friend. I was running out of time, so there's like the outline of like how I had tried to approach it in there, but that part of it doesn't work. So y'all are wondering, like, how do we do this? What does this look like? Well, it's a gen server. Sorry, it's gen servers all the way down. That's all that life is gen servers. So, but like it makes sense, right? Like we've used words like state and agent. We've talked about performing actions, so like executing functions. So it makes a lot of sense that the agent is going to be a gen server because it has to manage its own state. It has to manage that queue table, the quality of the state in action. Likewise, the gen server, it also needs, the environment gen server also needs to keep track of the current state, and it also has to compute rewards and compute next state. So gen server makes a lot of sense here. So let's talk about evaluating results. These are not good results. Looking at this, I'm sorry that this is so small, but this is like you start out at like having 100% of your money. I trained this on Yahoo Finance, which I did that on purpose because you don't want to do that. You want to find a better data set that gives you, price and volume information on a much shorter time window than daily. Ultimately, like if you're going to high volume trade, you want like minutely data, like at the most. But this one, at least in training, it ended up losing a little bit of money. But in evaluation over a year, this made simulated, I clipped the number of episodes so that way I could get it to run really quickly. But it makes like, 5 to 10%, at least like now. Now, there are ways to improve upon that. Really, where we get is that high volume trading like this is really looking at like, I'm going to hold this position not for long, not for very long at all, maybe even just a couple of minutes. So what you're looking for in that time is either an increase of like 1 to 2 cents in the stock price if you went long, or if you went short, you want it to go down that much. And in order to make money doing that, you have to trade a lot of stocks at a time. Like this simulation that I did, I was going long and short in blocks of 1,000. So at that point, like, you're making, at least tens of dollars, if it goes up like a couple of cents, right? But like ideally, like a hedge fund, they're going to trade like millions of shares, because then you're looking at like thousands of dollars in seconds. So it's like printing money. So if you want to make a lot of money, you have to have a lot of money. So have a rich dad. So also, if you look back here, I trained over a 2-year window, but I evaluated over a 1-year window. This is because models rot over time. You have to continually update them. If you evaluate on that same environment for 2 years instead of 1, it loses money. So every once in a while, you still have to update it and get through that. So these results, like it made a little bit of money. If I trained it longer, if I chose different stocks, I just chose like JP Morgan just because it's easy, and like during the pandemic, it like tanked really hard at the beginning. So I was like, I want some like not ideal data. But in looking at this in Elixir, like so much of machine learning research and development is done in Python, and we work in Elixir because we know that we can do better. So in looking at this in Elixir, like since these are gen servers, you know, you could distribute these because it's very important that the timeliness of these trades go through very quickly and that you make these decisions very quickly, because 1 second could be the difference between like making thousands of dollars or losing thousands of dollars. So that part is very important. We also, you know, I said it, we can do better. We like it. All right, that's it. That's what I got.